So for chapter 18, we are going to revisit thermodynamics, heats of reaction, but we're going to add a little bit to it, and we're going to relate it to equilibrium. So thermodynamics is the study of the relationship between heat and other forms of energy in a chemical or physical process. You may remember that we talked about enthalpy, or delta H, back in chapter 6. Enthalpy is defined as the heat of reaction at constant pressure. And now we're going to define enthalpy more precisely, and we're going to also introduce some other terms, entropy and free energy, and a few other things. So eventually we're going to talk about the laws of thermodynamics. There's 3 laws, actually 4 laws of thermodynamics, but in order to understand the laws of thermodynamics, we first have to understand the internal energy of a system and how energy changes. So internal energy is given the symbol U, and the internal energy is the sum of the kinetic and potential energies of the particles making up the system. So we know that kinetic energy is the energy of motion, and so that would include things like electrons moving, nuclei moving, molecules moving around. And then potential energy, we know, is the energy of stored energy, and so it is the energy that is found in chemical bonds, attractions between molecules, etc. So both of these types of energies make up internal energy of some system. So internal energy is a state function, one that depends only on its present state and not how it got to that state. So an easier example of understanding a state function would be altitude. So for example, if you were standing at the top of Mount Rogers, 5,700 feet high, if you're at the top of it, you're at 5,700 feet altitude. It doesn't matter if you climbed straight up the mountain, or if you drove up the mountain, or if you hiked and went round and round and round in circles all the way to the top, or if a helicopter dropped you at the top. No matter how you got to the top of the mountain, you would be at the same altitude. So altitude is a state function. It only depends on the present state and not how it got there. So it kind of, you can also think of Hess's law from chapter 6, where, we said the heat of the reaction is the sum of, so if you do the reaction in one step, you have a certain heat of reaction. If you do that same reaction in 2 steps, the sum of the 2 steps should equal the first step, the combined step. And so again, that state function doesn't matter how you got there, but where you are. Okay, so energy is actually a hard thing to pinpoint. You can't really measure energy, but it is pretty easy to find change in energy, and so that's what we usually talk about. We usually talk about the change in energy, or change in internal energy, delta U, which change of anything is always the final minus the initial. So if we measure the final energy minus the initial energy, we find the change in energy. And just keep some signs. Just keep signs in your mind. If it's a positive delta U, that means that the final is higher than the initial, which means you've gained energy. So that's, you're putting energy in. And then if delta U is negative, the system has lost energy. That means that your initial energy is higher than your final energy. And heat energy is one type of energy. So remember, we talked about endothermic being a positive delta H and exothermic being a negative delta H. Delta U is one part, delta H is one part of delta U. So heat energy is one kind of energy, but when we're talking delta U, we're talking about all the different kinds of energy possible. So kinetic energy of movement, attractions, potential energy, all of that. But it's the same idea. So we saw in chapter 6 that chemical changes usually result in the release or absorption of heat. And then we also talked in chapter 6 about chemical changes often causing work to be done. Not always, but they can. The work that can be done can be any or including these kind of work or others, electrical, nuclear, but the one we're going to focus on is mechanical work. All right, so again, changes in the internal energy show themselves as exchanges of energy between the system and surrounding. And like we said, these exchanges are of two kinds, either heat or work. So remember, again, this is from chapter 6. Heat is energy that moves into or out of a system because of a temperature difference between the system and surroundings. So heat is just energy moving because of temperature differences. And then work is energy exchange that results when a force moves an object through a distance. So in other words, work equals force times distance. So that's something like you think of a pulley. If you're moving a weight through space on a pulley, that would be one example of mechanical work. So we looked at this in chapter 6 too, but just a little bit of a review. So in this system, you've got a gas inside the piston, and if you heat it up, the heat, you're adding heat to it, so that's a transfer. That's a transfer because of temperature differences. So heat goes in, and then the gas has to expand because the molecules start moving faster, and because the pressure is not the pressure is held constant, the gas will expand, and it does work. So what happens is that piston will move from a lower level to a higher level, and that is a type of mechanical work. So let's just keep in mind the sign convention. So if work is done by the system, W, work is negative. If work is done into the system, on the system, work is positive. If heat is given off by the system, it's negative. And if heat is absorbed by the system, it's positive. So it's kind of important to keep your signs in mind. All right, so the first law of thermodynamics basically is the law of conservation of energy. So basically it says that energy cannot be created or destroyed. It can only be transferred. Okay, so when we apply this to a chemical system, that means that changes in internal energy can be made up of both heat and work. So remember, heat is Q and work is W. So internal energy, the changes in energy have to do with both heat energy changes and work changes, like we saw on that piston a couple of slides ago. So when the reaction is run in an open vessel, or in other words, at constant pressure, any gases produced then are a source of expansion work. So I think it'd be better to talk about it if we look at the picture on the next slide. The pressure, we're going to be looking at the type of work that gas does in a piston, and it's called pressure volume work, or PV work. But let's talk about it on the next slide. Okay, so here's a reaction, and we actually did this maybe back in first semester. If you put zinc in hydrochloric acid, we know that hydrogen gas is produced. So when we did it in lab, we had the vessel open to the atmosphere, so we actually weren't able to collect the work that was done by the gas. But if you can imagine it here, you can see that once the gas is produced, because this is at constant pressure, that piston, we're not putting more weight on it or anything, we're keeping that one weight, so that piston moves up. And so that is actually work that's being done. If you can imagine that if that piston was connected to some other dial or switch or something, that would actually produce some work that could be useful for something else. In fact, that's what's happening like inside your vehicle, is you're expanding a piston and it's connected to something else and it moves something else, and eventually that's how we use the work for something else. Also note that in this reaction, heat is being released. So again, thinking about that last picture, when the gases are produced, they exert a force on the surroundings as pressure. And if you're running the reaction at constant pressure, then the change in volume is analogous to the distance over which a force is exerted, which is the definition of work. And so we can actually calculate the amount of work that's done by using this equation. Work equals negative P delta V. Now, why is it negative? It's negative because the work is done by the chemical reaction onto the system, or the surroundings, by the system onto the surroundings. So that's why it's negative. And then P, because it's constant, is just the constant pressure. And then the delta V is the change in volume that happens during the reaction. Okay, so if we look at an example, let's say we had 1 mole of zinc reacting with excess hydrochloric acid. And if we start with 1 mole of zinc, then we're going to end up with 1 mole of hydrogen because it's a 1-to-1 ratio. As part of that reaction, we see that the delta H, or the QP, the heat of the reaction, is negative 153.9 kilojoules. That would be something that actually you could calculate by looking up the delta H values for this reaction and take the products minus the reactants, etc. But that's the amount of heat that's released, and that's the one we tend to think of as most likely as the energy, so the heat energy. But of course, there's actually other energy that is being produced, and that's the work energy. So if we look, let's say we're at 25 degrees Celsius and 1 atmosphere pressure. It could be any temperature and pressure, but we'll just take that 25 degrees and 1, which is sort of standard atmosphere and room temperature. So if you take 1 mole of any gas at 1 atmosphere and 25 degrees, then it occupies 24.5 liters. You can figure that out by using the gas law, the ideal gas law. Now they've converted atmospheres to pascals, and I'll tell you why in just a second. And then they've converted liters to meters cubed. So if you plug those numbers in for pressure and volume, so pressure is 1.01 times 10 to the minus fifth times 10 to the fifth pascals, and then you multiply by the volume, 24.5 times 10 to the minus 3 meters cubed. If you multiply that out, your units will be pascals times meters cubed. Well, pascals are actually kilograms per meter second squared. So if you multiply that by meters cubed, one of the meters cancels, and so you end up with units that are kilograms meters squared per second squared, which is also the same as joules. So that's why they've converted to pascals and meters cubed. So they're doing work, and that you figure out that the amount of work done by the system is 2.47 times 10 to the minus times 10 to the third joules, or in other words, negative 2.47 kilojoules. So heat is being given off and work is being done by the system. So now if we add them together, we see that the total change in energy is due to both the heat and the work. So most of it's from heat, negative 153.9 kilojoules being given off in heat, but also some of the energy change is due to work, negative 2.47 kilojoules. So the total change in internal energy is negative 156.7. So 156.7 kilojoules of energy of some sort is given off. So when the reaction occurs, the internal energy changes as both the kinetic and potential energies change in going from reactants to products. Energy leaves the system mostly as heat and partly as expansion work. Now, this one, obviously, the heat is being given off and the work is being done by the system, but the other things can happen. If it's an endothermic reaction, heat can be coming into the system. If you're doing work on the system, then work is positive, and so you can have any combination. This one just happens to be giving heat off and doing work by the system on the surroundings. So in Chapter 6, we tentatively defined enthalpy, delta H, as the heat given or heat at constant pressure, and the heat change at constant pressure. We can now define enthalpy precisely as the quantity U, internal energy, plus PV, pressure times volume. Why is that? We know that U equals Q plus W, heat plus work. Under the conditions, under constant pressure, we know that Q equals H, and we know that work equals negative PV. So U equals H minus PV. So if you rearrange this equation, we find out that H equals U plus PV. So this is just a new definition, and actually it's like we've talked about earlier, the delta H equals delta U plus P delta V is very much more useful because it's really hard to measure one of these quantities without looking at changes in that quantity. So the deltas are really much more important. Because U, P, and V are all state functions, then H is also a state function. Okay, so this means that at a given temperature and pressure, a given amount of substance will have a definite enthalpy, a definite H. So if you can know the enthalpies of the substances, you can calculate the change in enthalpy for a reaction. And we've done that back in chapter 6, so we know delta H. Remember from chapter 6, the standard enthalpy change for a reaction is delta H of all the products times their coefficient. You sum them all up. Always do the products first. And then take all the delta H's for the reactants, multiply them by their coefficient, and sum them up. And then you take the sum of the products minus the sum of the reactants. It's always final minus initial. Okay, now if delta H is positive, that means the reaction's endothermic. Heat is absorbed. In other words, the heat of the products is higher than the heat of the reactants. So you've put heat in. If delta H is negative, the reaction is exothermic, which means heat is released. That's because the reactants are at a higher heat than the products, and so heat was given off. Usually what we do is we tabulate enthalpies of formation. So you see that delta H of formation with the little sub f, and we can use these because of Hess's law. And so all the delta H's that you find at the back of the book are delta H's of formation, which means the delta H that it took to make that chemical from its elements. And those standard enthalpies are found in table 6.2, but probably better place for you to look is Appendix C in your book, because you'll see that they also have other values that we're going to use soon. So all of these delta H of formation are found in the back of your book in Appendix C. And remember, you take products minus reactants and make sure to multiply by their coefficients. And when you're doing these calculations, be really careful with negative signs and distributing. So what I recommend is total all the products, total all the reactants, and then do one number minus the other number. Okay, so we're going to talk now about spontaneous processes, and we're going to introduce a new quantity or a new unit called entropy. So a spontaneous process is a physical or chemical change that occurs by itself without having to do anything. What are some examples? Well, if you have the rock at the top of a hill, or think about, if you hold a rock above your head and you let go, what's going to happen? It's going to naturally drop. A rock at the top of a hill is going to naturally roll down to the bottom of the hill. Heat will always flow from a hot object to a cold one. That's the spontaneous thing that will happen without intervention. If you have an iron object in moist air, it's going to rust. That's a spontaneous chemical reaction that will happen. These processes all occur without requiring an outside force, and they'll continue until equilibrium is reached. So here's an example. Spontaneous process would be the rock coming down the hill. A rock rolling up the hill without help is a non-spontaneous process. Now, a reversible process is a change made on a system that can be restored by reversing the change. So, for example, you can take water at 0 degrees and you can freeze it by removing energy. But you can also take ice at 0 degrees and you can melt it by adding energy. That's a reversible process. An irreversible process is one that cannot be restored simply by reversing conditions. It has to take a different path to get back, or maybe not even possibly at all. So pushing a rock up a hill is an irreversible process. You can make heat from cold, but you're actually going to need to do work on it, for example, using a heat pump. Now, if a system is in equilibrium, reactants and products will interconnect reversibly. So if you're at equilibrium, you have a reversible situation. In a spontaneous process, the path between reactants and products is irreversible. And just note that a spontaneous process can be something that's slow and not necessarily observable. So, for example, a nail rusting is a spontaneous process. However, you may not see it happening at that moment, but if you leave it for a few months, you will notice that it happened. So when we look at a reaction, we say, will this reaction go as written? Basically, we're asking, is this reaction spontaneous? The first law of thermodynamics does not answer this question, and so we need to look a little further. So the second law of thermodynamics talks about spontaneity and introduces a quantity called entropy. Entropy, which is given the letter S as its symbol, is a thermodynamic quantity which is the measure of randomness or disorder. The unit for entropy is joules per Kelvin, and it is also a state function. So another way to think of entropy is as a measure of how dispersed the energy of a system is among the different possible ways that a system can contain energy. So that's kind of a mouthful. Just the more degrees of freedom is a term that we use sometimes. The more ways that a system can have freedom, the more entropy it has. So if the energy has few energy, if the energy is concentrated in a few states, the entropy of the system is low. If the same energy is dispersed or spread out over a great many energy states, entropy is high. We could think of a few examples. For example, the entropy of liquid water is higher than that of solid ice. In an ice crystal, water molecules are very fixed. They're within the lattice, so molecules can only vibrate just around these fixed points, but they're actually very restricted. But in a liquid, water molecules now can rotate, they can move, they have more degrees of freedom is a way of saying it. They can rotate, they can sort of move away from each other, they can vibrate, they can still do the same things that the ice does, but they have more opportunities to move around and rotate. And so the entropy of water is higher than ice because the energy is dispersed over more available energy states. Another example would be if you take a flask that's filled with gas molecules, and then you have attached to it another flask that's empty. If you open the stopcock between them, there's naturally the gas molecules will move into the vacuum and they'll spread out. So again, what's happening is that those molecules are able to be dispersed over a larger amount of space, and so they can move more. They have more degrees of freedom. Processes in which disorder increases tend to occur spontaneously. This is not always true, so notice the word tend, and we'll talk more about when it's not true. But for the most part, we think of disorder as something that happens spontaneously. If you just think about, I can think about my bedroom and how disorder increases quite spontaneously. You'll know what I'm talking about. For example, if you've got ice in at room temperature, so at 25 degrees Celsius, and it melts, the molecules become less rigid and can move more freely. So liquid is more random or less ordered than ice. So liquid has more entropy. And ice will melt spontaneously if it's at 25 degrees Celsius. If you dissolve a salt, what happens? The ions break apart and dissolve and dissociate, and so that is also more random than the solid. If you have a gas at high pressure, and you open the spout, so say you have a tank of gas and you open the spout, that gas will naturally move from that area of high pressure to lower pressure. That's a spontaneous thing that would happen. And you can see that it will increase entropy because the gas in a small container versus a much bigger area it will be much more disordered in the bigger area. So entropy is also a state function, which means a change in entropy does not depend on the path, only on the final and initial state. So you can see here that the change in entropy, delta S, is the S of the final state minus the S of the initial state. If delta S is positive, greater than 0, that means the final state is more disordered. There's an increase in disorder. If delta S is less than 0 or negative, that means the final state is more ordered and less random. And I want you to note that because it's a little bit different. Remember that delta H, a negative delta H means that it's exothermic, and a positive delta H means it's endothermic. And now the signs are a little bit different. So the thing that becomes more disordered is actually positive, and the thing that becomes less disordered or more ordered is negative. So keep that in mind. So the second law of thermodynamics says that the total entropy of a system and its surroundings always increases for a spontaneous reaction. If we define delta S of the universe as delta S of the system plus delta S of the surroundings, which is everything else besides the system, it turns out that entropy is not conserved. The delta S of the universe is always increasing. And this is just another way of saying that the universe is tending toward disorder. So for example, if you straighten your desk, it's more ordered than it was before, right? So the entropy of the system decreases because it's more ordered. But to achieve this, you move a lot of other things. You might make a mess in another location. Just the fact that your body is metabolizing food, putting off energy, moving around, again, is putting off heat. Overall, entropy is increasing for the whole system plus surroundings. So the first law of thermodynamics is more about the total quantity of energy. Energy can't be created nor destroyed. The second law of thermodynamics is more about the quality of energy. What that means is as more and more heat energy is transferred, and that's going to happen because of life. We've got heat in our body that is we're giving off heat as we even just sit still. As more heat energy is transferred or transformed into entropy, less and less of it can be used, and so more of it is wasted. So let's look at the oxidation of iron. First of all, if you look at the equation, you can see that this is also a decrease in entropy. How do I know that? Well, just kind of in general, I look on the left-hand side of the equation and there's 7 molecules. On the right hand, there's only 2. So clearly, it's becoming more ordered because you've put 7 things and made 2 things. Also, another time, sometimes we also look at it and we think of oxygen or gas in general. Gas tends to be more disordered than solids or liquids. And so a lot of times when we want to look at an equation to see what's happening, we look at the number of gas molecules. And in this case, we start with 3 gas molecules and we end with none. So again, this is becoming more ordered. However, this reaction of rust happening on a piece of iron, is exothermic. So again, like I was saying on the previous slide, the entropy of the surrounding increases because the heat is being involved. The heat is making molecules move faster. There's more thermal motion in the surrounding molecules, so entropy is increasing. So even if in the system it's decreasing, the surroundings is generally increasing. Another example that I just read about, what if you take a salt solution and you evaporate it? So you're saying, well, okay, that salt solution has now become a solid. So again, that it's gone from dissociated ions to a solid salt. But what are you doing in the process? Well, you're having to evaporate the water. And so taking that liquid water and making it vapor water has increase the entropy so much more that it compensates for the decrease in entropy of the salt, but in fact there's more of it, and so again overall entropy is increasing. So no process that produces order in a system can proceed without producing an equal or greater disorder in its surroundings. Okay, so when we have a spontaneous process carried out at a given temperature, the second law can be restated. That refers only to the system. Now, the total entropy of an isolated system can only increase over time. Remember, when we're talking about a spontaneous process, we're talking about an irreversible process, and so entropy can only increase. It is true that entropy can remain constant in ideal cases where the system is in equilibrium or undergoing a reversible process, but in reality there are technically no reversible process, so most all reactions are spontaneous or irreversible. So as this irreversible spontaneous process occurs, the entropy is increased, and at the same time heat might flow into or out of a system. Entropy is produced because of the spontaneous reaction. The heat flow is also an entropy change because it's a dispersal of energy. And so this entropy change is associated both with heat at a particular temperature. So it turns out that the change in entropy of the system, delta S, equals the sum of the entropy created during the spontaneous process plus the change in entropy associated with the heat flow, which is that Q divided by T. So delta S equals entropy created plus Q over T for a spontaneous process. So it's usually hard to estimate the quantity or to calculate the amount of entropy created during a spontaneous process. So if we delete it from our equation, we can see this instead, that since delta S equals entropy plus Q over T, since we know some entropy is being produced, then we can at least say the delta S for the system is greater than Q divided by T. So we can restate the second law as follows. For a spontaneous process, the change in entropy of the system is greater than the heat divided by the absolute temperature. And heat, remember, is related to enthalpy. If you have a phase transition, this is the closest that we get to a reversible process. So a phase transition such as ice melting, in this case, heat is slowly absorbed by the system, and so it remains very near equilibrium, and so this is considered a reversible reaction. And so under these conditions, entropy is not created. So again, this is not a perfect system, and so actually there might be a little bit of entropy created, but under a true reversible situation, entropy is not created during there is no real reaction. There's no entropy created. So in this case, we can say that any entropy that results is entirely from this heat transfer, or Q over T. So for an equilibrium process or a reversible process, delta S equals Q over T. So and this can happen in any phase change, so like as ice melting. It also could occur in a vaporization of a liquid, in other equilibrium conditions, but basically phase changes are the main ones. So we can use that previous equation to find the entropy change for a phase change, which we'll do in just a second. So let's look at an example. The heat of vaporization, delta H of vaporization for carbon tetrachloride, is 43 kilojoules per mole. If we vaporize 1 mole of liquid carbon tetrachloride, and that liquid carbon tetrachloride has an entropy of 214 joules per Kelvin, what will the entropy be of the vapor at this temperature? So we can actually calculate delta S, the change in entropy. So delta H is 43 kilojoules per mole, or 43,000 joules per mole, at 25 degrees Celsius, which is 298 Kelvin. And so the entropy change, delta S, is equal to 144 joules per mole Kelvin. Okay, now that's the entropy change. So in other words, 1 mole of carbon tetrachloride will increase in entropy by 144 joules per Kelvin when it vaporizes. So if the entropy of the liquid is 214, then the mole of vapor will have to add 144 to it. So in other words, delta S is equal to S final minus S initial. The S initial is 214. The delta S is 144. So our S final will be 358 joules per Kelvin for 1 mole of carbon tetrachloride. So hopefully, if you keep taking something and you keep making it more and more and more and more ordered, so that you have a perfectly crystalline compound that is totally motionless. So if it has an entropy of 0, you have gone all the way down to 0 degrees Kelvin, which is absolute 0. So basically, absolute 0 means absolutely no movement at all. So the third law of thermodynamics says that a substance that is perfectly crystalline at 0 degrees Kelvin has no entropy. And so what happens then, if you heat it even just a teensy bit, even like 0.1 degree Kelvin, just increase it just a teensy bit, the molecules will start moving. So they start to become just a little bit more disordered as that heat is absorbed, and so entropy increases. So the entropy of a substance is determined by measuring how much heat is required to change its temperature per Kelvin degree, which is what we saw earlier. Delta S is heat per temperature. So this kind of links the laws together. So the standard entropy of a substance or an ion is also called its absolute entropy, as given the symbols S naught because it's standard, and it's the entropy value for the standard state of the species. So what does that mean? Standard state generally means that it decrease. Now it's not always hard fast rule, but in general this is very helpful. And then also, if you have a process which changes from a solid to a liquid, or a liquid to a gas, or a solid to a gas, you can see that all of those are increasing their entropy. They're all getting more disordered. So sometimes we can predict the sign even before we calculate it. So in these examples, tell me if delta S is going to be positive, meaning an increase in entropy, or negative, meaning a decrease in entropy. H2O liquid to H2O gas. Okay, so we are increasing disorder because we're going from a liquid to a gas, so delta S should be positive. Okay, silver ions plus chloride ions precipitate to form silver chloride solid. Well, now you can see that we've got them aqueous, two ions separate from each other, and then on the other side they come together, so that's becoming more ordered, so that is a decrease in entropy. Delta S should be negative. We already talked about this one a little while ago, but iron reacting with oxygen to give us rust. Again, you can sort of see that there's 7 molecules on the left going to 2, so that's becoming more ordered. Also, we have 3 molecules of gas going to 0 molecules of gas, which is becoming more ordered. So again, delta S should be negative. All right, let's calculate the change in entropy at 25 degrees for the reaction in which urea is formed from ammonia and carbon dioxide. If you look, we can look up all the values in the back of the book. If you looked back there, you would not find the standard entropy for urea, NH2CO, NH2, so it's given to you in this problem, and that will always be true. If it's not found on the chart, it'll be given to you. Okay, so the standard entropy for urea is 174 joules per mole Kelvin. Look up the other values in table, should be table 18.1. All right, so if I look, and the calculation is similar to what we did for delta H. So I look up the entropies, and a lot of times I like to put them underneath the formula just to keep track of them. So the NH3 is 192, CO2 is 214. Urea, as the problem tells you, is 174, and H2O, and be careful here, make sure that you look up the correct phase, because you're going to find H2O liquid and gas. You might even find solid, so make sure you have the correct one. For liquid, it's 70. All right, don't forget that you have to multiply by the coefficients, and so delta S is always going to be products minus reactants. So take the products times their coefficients minus the reactants times their coefficient. So in this case, we have the products, urea 174 plus H2O 70 gives us 244. And then we have the reactants, 2 times 193 plus 214. So if you take those and subtract the second one from the first one, you get negative 356 joules per Kelvin. And let's just think about that for a second. We have 3 gas molecules on the left-hand side. We have 0 gas molecules on the right-hand side. So already, and also, just in general, we have 3 molecules on the left, only 2 on the right, and you can see that we're forming something that's much more complex looking. So clearly our order is increasing. We're making this more ordered, and so we do expect a negative delta S, which is what we got.